Welcome to this video, the first of a 3-video series on oceans and fisheries. I'm Aida Awad from Broward College. The learning targets for this video are to compare the patterns of ocean surface and subsurface currents, to identify variables that control global surface ocean currents, to explain how the Gulf Stream impacts weather patterns along the east coast of North America and Western Europe, and to compare and contrast wind patterns, currents, air masses, and precipitation patterns associated with normal, El Nino, and La Nina conditions. We'll start out with surface currents. In the big picture we can see here is that there are two different types of surface currents. There are warm surface currents and there are cooler surface currents. The red currents are shown as warm and the blue are the cold. Now, surface currents are typically produced by winds, and the main surface ocean current pattern is in a clockwise direction in the northern hemisphere and in a counterclockwise direction in the southern hemisphere. And this is a result primarily of the Coriolis effect, which deflects particles in the northern hemisphere to the right into a clockwise motion, and in the southern hemisphere to the left into a counterclockwise motion. We see this in more detail for Atlantic surface ocean currents, where the tropical trade winds blow east to west and the mid-latitude westerlies blow towards the east, which establishes that clockwise gyre that's known as the North Atlantic equatorial current. The current is then deflected northward along North America's east coast and then heads out to sea towards Europe. The current splits with a northern-bound leg, the Norway current, heading up towards the Arctic, where it meets up with the Arctic Ocean currents, and a southern leg, the south-flowing Canary current, that brings it back around to meet up with the North Equatorial current. We turn now to thinking about the vertical mixing of ocean water, which causes the deeper ocean currents. The density of seawater helps to drive these deep ocean currents. In fact, cold, salty water is denser than warmer, less salty water, and this sets up the ocean meridional circulation. That's the sinking movement of the cold, salty water shown in the picture here in blue that generates those deep ocean currents, and it returns back to the surface as warmer water shown in red, which completes the loop. So again, the Coriolis effect has an impact here. In fact, it has a stronger impact at depth in the ocean and causes those deep ocean currents to travel in a different direction than the surface currents. Global circulation of shallow and deep currents is what's known as the ocean conveyor belt. And the ocean conveyor belt impacts regional and global climates. Let's take a look at the Gulf Stream here. The Gulf Stream current is the western boundary current of the North Atlantic gyre. We've seen the North Atlantic gyre here. We're on the west edge of it. And it's part of the ocean conveyor belt. The Gulf Stream acts to transport heat from the equatorial or subtropical regions northward. It's typically about 90 kilometers in width and has a peak velocity of 5 knots, which is about 2 meters per second. In the picture on the left side, you can see arrows that indicate the direction of that Gulf Stream current shown in a white color. And in the picture on the right side, you see a white arrow indicating that the Gulf Stream current moving north and then eastward towards Europe splits into the Norway current and the Canary current, which completes the loop. Now turning our attention to look at situations that are atypical. So we'll compare normal situation with the condition of El Nino, and then we'll come back and talk about La Nina afterwards. We know that winds from the atmosphere affect ocean currents, specifically the surface current. And we know that heat from the oceans affects the atmospheric circulation. Well, in the El Nino's Southern Oscillation, or ENSO, there is a periodic and large-scale warming of the surface waters of the tropical eastern Pacific Ocean, which is up against the western coast of South America. And that temporarily alters both the ocean and the atmospheric circulation patterns. The El Nino happens roughly every 3 to 7 years, And when it does, it weakens the trade winds with that warm mass of water expanding to South America and makes those surface currents warmer in the eastern Pacific. Ocean currents then slow down during an El Nino, and El Ninos typically last from 1 to 2 years. So we can see in the diagram above the formation of an El Nino. So in the normal condition, we have the accumulation of warm water on the western portion of the Pacific, and that's a result of the west-flowing trade winds. The warm, moist air rises up towards the north area, which cools it and causes high pressure and a little bit of rainfall. In this situation, up against the western coast of South America, there is an upwelling of nutrient-rich water. That's cold water, and that's called the Humboldt Current. Now, in an El Nino situation, those west-flowing southeast trade winds don't blow to the west. They weaken. In fact, warm water flows from the western Pacific towards the eastern Pacific and up against the western coast of South America. That causes the warm air to rise and low pressure and heavy rainfall along some parts of North America and South America. And that warm water blocks the upwelling of the cold Humboldt currents, forcing warm water up against the coastline of South America. So we can see in this slide another depiction of the El Nino, but this time we're focusing in just on the west coast of South America. So in the picture on the left side, we see the normal situation where cool, nutrient-rich waters upwell against the surface, and that's the Humboldt Current. And those strong trade winds blow away from shore, pushing the warmer water off towards the western Pacific. But in an El Nino, the warm water stays along the coast because the trade winds are weakened, and the nutrient-rich cool waters remain at depths offshore. That has an impact on South American fisheries. In fact, in 1997 and 98, there was an El Nino that caused about 20,000 deaths and about $33 billion in property damage. Caused significant snows in the western U.S., ice storms in eastern Canada, torrential rains along the west coast of North America and along the west coast of South America, and droughts in Texas, Australia, and Indonesia. Recently, NOAA, the National Oceanic and Atmospheric Administration, has established 2 arrays of buoys, comprised of about 70 buoys total in the Pacific Ocean, that monitor temperature and monitor winds, and these are used to help forecast El Nino events. The opposite of an El Nino is a La Nina, and La Nina events often, but not always, occur after an El Nino event. In a La Nina, the westbound trade winds become unusually strong, and that pushes the surface water temperatures along the eastern Pacific back to the cooler range. The impact on global weather patterns is as follows. We have typically wetter than usual winters in the Pacific Northwest portion of North America, warmer weather in the southwestern portion of North America, and oftentimes Atlantic hurricanes are stronger and more numerous. I think we can go back to our learning targets and think about our mastery quiz. Learning targets were to compare the patterns of ocean surface and subsurface currents, identify variables controlling global surface ocean currents, explain how the Gulf Stream impacts weather patterns in and along the east coast of North America and Western Europe, and compare and contrast wind patterns, currents, air masses, and precipitation patterns associated with normal, El Nino, and La Nina situations. Go ahead and take your mastery quiz, and I'll see you in class.